In this unit, we will take a closer look at the three-dimensional structure of compounds. In particular, we will explore compounds that differ not in the connectivity of their atoms, but in the 3D spatial arrangement of their atoms. We will first review what are isomers, and eventually end up talking about what are known as stereoisomers. To understand stereoisomers, we will introduce to the concept of chirality, of mirror images, and of enantiomers. Finally, we will end up with a little detour in what is known as Fischer Projections. So we will start this chapter with a brief overview of what is isomerism. So it comes from the Greek for made of the same parts. You see the root word iso there, that means equal or the same. And in the context of organic chemistry, we will compare molecules that have a certain relationship to one another. And because of these various relationships, they will be called isomers. So these molecules share certain qualities with each other. They are somehow made of some equal parts. Now, we've seen different types of isomers before. We've seen what's known as a constitutional isomer, and hopefully you would recall that constitutional isomers are compounds that share the same formula but are different in the way the atoms are connected to one another. For example, we know that this ether and this alcohol are constitutional isomers of each other because they have the same chemical formula. They both have 2 carbons, 6 hydrogens, and 1 oxygen. However, these atoms are arranged in different orders to make an ether or to make the alcohol. And therefore, these 2 molecules are completely different from one another, but they do share that same formula, so they are called constitutional isomers. There's another type of isomers. It is called stereoisomers. And stereoisomers have the same formula and the same connectivity. However, even though those atoms are connected in the same order, they have, however, different spatial arrangements. And in fact, we have already seen one type of stereoisomers already in a previous section. We recall back when we were looking at cycloalkanes and we were introduced to the concept of a cis and trans isomers. So in fact, these 2 molecules have the same chemical formula and they have the same connectivity. However, at that 1 carbon that I have highlighted in red, the way that the methyl group is spatially arranged is different between these 2 molecules. In the cis compound, we see that the methyl group is coming out of the plane, so it is a wedge, whereas in the trans molecule, we see that the methyl group is a dash going away from us and into the plane. And that slight difference in 3D arrangement makes these 2 molecules completely different from one another. They are distinct compounds, and their relationship is that they are stereoisomers of one another. Let's take a look at another example of stereoisomers. In this simple 4-carbon compound, we can see the concept of stereoisomerism. What we have here are 2 butenes. The molecule on the left is considered the cis isomer, and a molecule on the right is considered the trans isomers. And again, they are completely separate molecules. Contrast that to this next set of skeletal structures. I've drawn 2 representations of butane. However, these 2 skeletal structures are actually the same molecule. Just because on one side I have the methyl coming up and on the other side the methyl coming down, it seemingly on paper makes them look like they are different molecules. But that's not the case because we know that the single carbon-carbon bond can easily rotate, and as it rotates 180 degrees, the methyl that is coming down can be a methyl that's coming up. And so therefore, in fact, these are the same compounds. They are just in different conformations. Remember that in the previous chapter, we talked about conformations of linear alkanes. So why is this not possible for the set of molecules above, the alkene analogs? And the reason is because in the cis and trans alkene, we have a double bond. And double bonds are not free to rotate, because as you rotate them, you would have to break the pi bond. Remember, there is a side-by-side p orbital overlap between the 2 central carbon atoms. This p orbital overlap creates that pi bond. So if you were to rotate it, then you will no longer have that overlap. So therefore breaking a pi bond. And the breaking of that pi bond is too energetically costly, so the molecules will not do that at room temperature. If you are a cis molecule, you will be frozen as a cis molecule. If you are a trans molecule, you will be stuck as a trans molecule. In fact, one strong evidence that these two molecules are different molecules is that you can isolate them and observe their different characteristics. For example, the cis alkene has a boiling point of 4 degrees Celsius, whereas the trans isomer has a boiling point of 1 degree Celsius. Alright, so there we have it. We have established this concept of stereoisomerism, and we have seen this definition in the cis and trans relationship. But it turns out there are other types of stereoisomers, and we will heavily focus on them in this unit. So let's explore them by taking a look at mirror images. So take any object. In this case, we'll take a look at sunglasses. Put it in front of a mirror, and you would have its mirror image. Now, its mirror image in this case is identical to itself. What I mean by that is if you take that mirror image and imagine that it is an actual object, if you take that and you merge it together with the original object, they will overlay onto each other completely, perfectly. It's like one dissolves into the other completely. So it is no longer the case, however, if we take one of the lenses out. In this case, the mirror image is no longer identical. The original object has a lens on the left side, whereas its mirror image has the lens on the right side. Let's go back to our first case. When your mirror image is identical to yourself, we call that superimposable. Again, because the object can be overlaid onto one another, one object will disappear into the other. Whereas the case on the right-hand side, with the missing lens, these two objects are non-superimposable, where the mirror image is not identical to the original object. Another example of this are your left and your right hands. Take a look at them. Put them in front of you as if one is the mirror image of the other. However, can they be superimposed onto one another where one melds into the other, right? Completely disappear? You cannot, right? Another way of thinking about this, if you had a glove for your right hand, can you put it on your left hand? You cannot, right? And actually, because of this, we say that objects that have non-superimposable mirror images are called chiral, which comes from the Greek word for hand. So there's this handedness in the relationship of this object and its mirror image. And in fact, molecules can also be chiral. And we will spend the rest of this chapter looking at the chirality of molecules. And because this is an organic chemistry class, we will pay a special attention to carbons. And it turns out a molecule where there is a carbon with 4 different groups attached to that one carbon will have this property of chirality. Here is a simple example where I build a molecule with a tetrahedral carbon. And there are 4 different groups attached to this carbon. And then I also build its mirror image. Notice that there's no way that I can merge these 2 molecules together where one disappears into the other. And so because of this, carbons with 4 different groups are chiral, and these carbons are called chirality centers. And because organic chemists love to have multiple names for the same thing, you will often hear these interchangeable terminologies for the same concept. Sometimes it's called chirality center, sometimes it's called chiral center, or stereo center, or stereogenic center, or asymmetric center. And all these centers can also be interchanged with the word carbons. It could be an asymmetric carbon, a stereogenic carbon, etc. So we'll ease into this topic by first being able to recognize the chiral centers. Right? So in this first example, so recognize that this carbon, you have a chlorine that's coming out, but also a hydrogen that is not explicitly drawn in. So hydrogen is your second different group. Your third different group is that methyl on your left-hand side and that ethyl group on your right-hand side. So it does have 4 different groups coming from the same carbon atom. Okay, so how about this molecule? This carbon on top is your chiral center. For the same reason, you have 4 different groups attached to the same carbon center. The OH is your first group. That hidden hydrogen, again, is your second group. The third and fourth group might seem like they are the same thing because they are attached to each other. In fact, they are not. And what I mean by that is if you go to the carbon onto your left-hand side, you have there an sp3 carbon, and that sp3 carbon is connected to another carbon and two hydrogens. Whereas the carbon on the right-hand side is an sp2 carbon, and that sp2 carbon is connected to a hydrogen and another carbon. So technically they have different identities right there. So because of that, that central carbon atom sees four different looking groups, even though the last two groups are actually connected to each other. But immediately in what it sees right in front of its face is that they are in fact different. It doesn't see that they are eventually going to connect. How about this molecule? Hopefully you said this is not a chiral molecule, because that carbon that you might think is a chiral center is not a chiral center, right? It has the chlorine and hydrogen are two separate groups. However, its third and fourth group are identical to each other. As you go on the third group here, you see hydrogen, a hydrogen, and a carbon, a hydrogen, and a carbon on the right-hand group as well. And then you keep on going, and you see that the next group is also a hydrogen, and a carbon, a hydrogen, and a carbon. So in fact, as long as you keep on tracing it out, the two groups are identical to each other. So you do not have four different groups coming out of that central carbon atoms. So there is no chiral centers, and this molecule is not chiral. In fact, it is called achiral. As a point of clarification, if you do not have a chiral center, you are definitely achiral. On the flip side, if you do have a chiral center, your molecule may not necessarily be chiral. So there is that caveat that we will explore in later videos. So let's continue with the practice of identifying chiral centers. Let's take a look at this first example molecule here. We have ascorbic acid, which is vitamin C. Can you identify the chiral centers? Remember, the key is to find that sp3 hybridized carbon with four things coming out of it, four different things, right? So at this carbon atom, is this a chiral center? No, right? Because there's two hydrogens, so those are identical groups. What about this carbon here? Does it have four groups? Indeed it does. It has this group, the OH, and then that last undrawn hydrogen. So that's four different groups. Okay, so that's our first chiral center. How about this next one over here? Does it have four? Yes, it does, right? So it has this big group here, this group, and then that undrawn hydrogen. So indeed, it is a chiral center. What about this carbon here? You might be tempted to say it is a chiral center because everything that it is attached to are different from one another, right? So it has this attachment up here, this attachment, and this attachment. All three groups are different from one another, right? But remember, you need to have four different groups. Because of this double bond, it does not have another hidden hydrogen to make it a fourth different group. So in fact, this is not a chiral center. So none of the sp2 or sp hybridized carbons will be your chiral centers. So that's all we have for this molecule then, two chiral centers. All right, so take a look at this steroid molecule here. Can you identify all the chiral centers in this molecule? So pause this video and try to do this on your own. All right, I'm gonna go ahead and take a look at it from the bottom up. So I see one chiral center here, one right 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 here, and one right here. So this molecule has 8 chiral centers. So now that we can identify chiral centers, let's go ahead and introduce some terminologies. So when a compound is chiral, its mirror image is called its enantiomer. They are enantiomers of each other. So again, the key here is that that molecule must be a chiral molecule. So let's go ahead and practice drawing enantiomers, or in other words, drawing mirror images of a molecule. Okay, so we have here amphetamine as our example. Hey, so there are many ways you can draw a mirror image of something. So I'm going to show you two ways. First, if you were to imagine that there's a mirror image on the side, just like the sunglasses example we saw earlier. So if you were to draw the mirror image from the side, this would be the mirror image of amphetamine. Notice at the chiral center, there's no change in that wedge methyl group coming out. It is still a wedge methyl group. However, what's on the left and right hand side are switched. So again, that is if you're taking a mirror from the side of the molecule. What happens if you have the mirror be in the back of the molecule? How would you draw that mirror image? So if it's from the back, you can see that that phenyl group stays looking the same, and so does that NH2 group on the side. At the chiral center though, notice that that methyl group is coming out of the paper, right? So in the mirror image, it would appear to go away. So in this case, there's only a change in that wedge and dash structure, whereas the two sides are the same. So in fact, these are two ways to draw a mirror image of amphetamine. However, these two mirror images are actually identical to each other. Okay, so that's the rule here. From a chiral molecule, if you draw different mirror images of that same chiral molecule, the mirror images themselves are actually identical to each other. You can try to convince yourself of this fact. Take these two mirror images. Let's say take the side mirror image. If you do a pancake flip of this molecule 180 degrees, you would actually get this molecule back. When you do a pancake flip of this molecule, that NH2 group on the left is now on the right, that phenyl group on the right is now on the left, and that methyl group that's wedged out is now going away as a dash. Alright, so we will leave it at that for now. Go ahead and have more practice in drawing mirror images and enantiomers. In future lessons, we will take a closer look at this relationship. But for now, we'll take a little detour into what are known as Fischer projections. Seemingly, this topic will not relate much to what we're learning here, but it's one molecular representation that is heavily used to depict with chiral molecules, so which is why we'll need to be familiar with them. And they are very often used in biochemistries because most of the times they're used to depict sugars with different chiral centers. I'll show you some examples of Fischer projections. These are all molecules of stereoisomers of the sugar glucose. What they differ in are the various chiral centers. So these flat lines here don't actually mean the same thing as they do in our bond line structure. So we need to be able to convert them first into a bond line structure format. How do we do that? We'll just take a look at a simple case. We have here a horizontal line where on the left-hand side you have HO, on the right-hand side you have H. On the top of this vertical line we have ethyl, for example, and then methyl at the bottom. Again, they are not simple line wedge structures, they are actual Fischer projections. So we'll then convert this into our more commonly recognizable bond line structure. So the rule is any horizontal line in the Fischer projections represents bonds that are coming out of the plane, so it is a wedge. And any vertical line in a Fischer projection represents bonds that are going away from us with a dash. Okay, so I'll represent this here with this molecule, this 3D model set. Okay, so this is what you are actually looking at. Two things are coming up at us and two things that are going away from us. But this way of representation, again, is not what we are familiar with. We are usually familiar with two bonds that are in the plane and two that are not, right? So we can twist this molecule like so to make any two bonds to be in plane. Let's do it again. Notice that when we twist that molecule, the bond that are up facing us stays facing us. The bond that is going away from us stays going away from us. Okay, so let's translate that into this projection. So if we do that kind of rotation, just choose any bond. In that one example, I chose the two left one to be in the plane and the two other two to be as they were. Okay, so there you have it. That's a structure in the representation that we are familiar with. Two in-plane lines, one wedge, and one dash. You can rotate this in any way you want to, really, as long as you have two bonds that are in the plane. So let's do that again. we would see that again the methyl is straight down. Now the hydrogen is in that in plane. The OH is now your wedge, and the ethyl is your dash. All right, so we'll leave it here for now. Practice drawing your Fischer projections and the translation of your Fischer projections. We'll come back to Fischer projections in the next video.